Okay, so continuing on, again, I'm going to skip some of these introductory slides and go to the topic, which is distribution system economics. So, in the morning, we talked about planning, and any kind of plan requires money. You have to buy equipment and you have to invest in terms of investment. You want to find out what are the benefits of what you're trying to do. So there is a cost and there is a benefit. So economics has to be taken into consideration. So what we're going to do is we're going to talk a little bit about economics. So just quickly show you or raise your hand if you know anything about economics. Any undergraduate classes that you took? Some of you have had some exposure. Okay, so maybe this will be something new to a lot of you, but I think it's for being an engineer, we feel like economics is not important, which is one of the things that I felt when I did my undergraduate degree and we had zero economics. But then when I started working, I realized that, oh, I should have learned something about it. So engineering always, because any engineering project, you need to find out the benefit, cost and benefit. So economics becomes important. Okay, so hopefully you'll be able to get some information today based on that. So the reason why it is important is that, if, as an example, let's consider that a utility decides to install capacitors in the system to improve power factor, and also when you do that, capacitors also reduce losses in the system. And then you want to say, okay, how much is the cost of the capacitors? So you account for that, and then you say how much are the benefits. So every year you are going to have some benefit which will be in terms of reduced losses. But the amount of benefit that you're going to get in the first year and what you're going to get the next year, assuming that the rate of electricity remains the same, is going to have a different value. For example, the money does not remain the same, it changes value over time. Because you put money in the bank, you get interest, so whatever you put money today, 100 rupees will become something else. So same thing happens in utility, electrical distribution systems. Whatever your benefits are today are not the same as the benefits you're going to get 10 years from today. So you have to account for all those benefits and compare them with respect to what is the value today of those benefits. Otherwise, if you consider 100 rupees from 10 years from today versus 100 rupees today, they are very different from one another because you're not going to be able to buy same things. It will be very different. So that's why we have to look at some basic economic principles, and that will allow us to do some comparison in terms of engineering decisions. So looking at some basic concepts, now keep in mind that the inflation is something different, because inflation is something, the cost of goods keep going up, which is different from interest. The bank is giving you an interest on the money which is not the same as the inflation. Inflation is completely different. Inflation is just a natural increase in the cost of goods. So in general, what happens is that it's a very complex thing. It's very difficult to predict inflation, what's going to happen next year, and let alone talk about 5 to 10 years from today, because the inflation is based on so many factors, the social factors, political factors. Like, for example, when we had COVID, right after that, things became more expensive. Did it happen here in India? I guess same thing. The supply chain got messed up, getting harder to buy things. And similarly, if you have things coming from other countries, for example, from China, and then somehow India and China decide that they don't want to buy things from one another, the trade goes away, and then everything becomes more expensive. So it's just so many things we cannot predict those things. So usually we don't bother about inflation in our calculations. We simply ignore that because typically what happens is that even if you include inflation in what you're trying to do is you're trying to compare two options. And if you can do the calculations for both of them, one turns out to be more expensive than the other. And if you can get the same answer without including inflation, then your calculations are much simpler and you get the same answer. So it doesn't make sense to worry about it. So typically we don't include inflation in our calculations. But what we include is something called discount rate. Now, this discount rate is actually different from interest rate because interest rate is something the bank is going to give you when you put money in the bank. They give you some interest for your money, and that interest depends on what type of account you have. If you put money in savings account, you get different interest versus putting money in a CD. It'll probably give you more interest because one of the conditions in CD is that you cannot withdraw the money and before the term is over, like 1 year, 2 year, whatever the term is. Now, the discount rate idea is very similar to interest, but it is different because when businesses take money from the bank, it includes other factors. For example, the risk, government policies, and other business factors. So, for example, if you have want to start a business and you want to borrow money from the bank, then you don't have any track record of doing any business. You are completely new. So the bank doesn't trust you very much because they have a risk that they might lose money. So they're going to give you money at a higher rate. And on the other hand, if somebody goes to borrow money with a very good track record of borrowing and repaying and you have a good credit, then your discount rate bank is willing to give you money at a lower rate. So this discount rate is what businesses use, and this typically includes a lot of other factors. But in terms of mathematical calculations, it's just like considering interest. So when you do calculation for money from 1 year to the next year, we simply consider that as the number. So for example, 100 today, if we have a 12% discount rate, which is same as considering it as an interest, then in 1 year it will become $112 because you get $12 as your interest. But in this case, it's really not interest. It's more like a kind of like charges on the money. Okay, so if we look at some mathematical relationships here, then this is what happens when you look at time value of money. And so we consider what we call as the discount factor, present worth factor or discount factor, which is equal to 1 over 1 plus d raised to power n, where n is the number of years and d is the discount rate. So for example, 12%. So make sure that d is in fractional number. It's not 12% essentially means 0.12. So in the calculations, although we say d is 12% discount rate, but in the equation you don't put 12, you put 0.12. So this is important. So let me write down here. For 12%, d is equal to 0.12. So, and then of course, depending on how many years, if you put 5 years there, then you get a number of 0.567. For 1 year, it's 0.893, which means that 100 years from today, uh, 100 years, one year from today, will have a present worth of 89.30. So if you have 89.30 today at 12% discount rate, it will become 100 next year. If you have $56.70 today, 5 years from today, it will become $100. Okay. So, and then annuity is something that defines an outlay, financial outlay that occurs at a fixed interval of time. So typically annuity applies to 1 year. So every year you have some payment, for example, or you're getting some benefit every year, same fixed amount of money. So typically a fixed amount on yearly basis. So for example, if you take a loan from the bank to buy a car, then you're going to pay a fixed amount of money every month. The same thing happens in engineering applications. We typically do it from a yearly basis. So for example, you have some equipment and you have to maintain. So every year you have to invest certain money for maintenance. So that's whatever is the amount of money that is fixed for on a yearly basis, we call that as annuity. So if you have, for example, you have $A being spent every year for N years, then we want to know what is the present worth of that money. Okay, so because typically the engineering projects will have a time period of 20 years or 30 years based on the life of the equipment. For example, if you want to install a solar panels in your house, you typically will consider 30 years, 20 years, because 20 years panels will probably not work anymore. So you consider lifetime of panels to be 20 years, and then you say, okay, every year I'm going to save so much money. So what's the total benefit for me in today's dollars? And then you also know how much money you're going to invest to get that. So you can compare what you invested versus your benefit. So in this case, what happens is that we consider $A next year, year after that, every year until N, capital N years. So this is the total PW present worth over a period of N years, and we add these things. Okay, so considering that A remains the same from 1 year to the next, that doesn't change. Okay, so we add them up, and now we can see that if we let 1 over A plus D equal to small a, then this equation becomes like this. And then what I have done here is I have added A and subtracted A. Okay, just for convenience. I'm going to tell you why. So you subtract add A to it and subtract A from here. Now this quantity right here in the middle from here to here is a geometric series. It's a finite geometric series. You can take a sum of, you can find, go to high school algebra class when you take the sum of series, geometric series, arithmetic series, all those things. So this is a geometric series. So this is something you probably already know from your high school things. So, and then this summation is whatever is inside the parenthesis is equal to this quantity right there, and then you substitute that here and then simplify that, so this comes out to be the equation which gives you the present worth of $A over a period of 30 years. Okay? Again, this is because the value of money does not remain the same from 1 year to the next. Okay, sometimes you have a situation where things are going to increase. In this case, we consider A remains the same. But what if this A keeps increasing at a fixed rate? Okay, by 2% or 3%, whatever. So in that case, what do we do? So let's assume that it increases at a rate of J. So like for example, load will increase at a rate of J. So losses will increase along with the load, because load is higher, so losses will be higher. So this, let's assume that the rate of growth is J. So from 1 year to the next year, the value of A will change by a quantity that is multiplied by 1 plus J. Again, in this case, J is a fractional number. So if you have 2%, then it's 0.02. Okay, don't put 2 there, it's a fractional thing. And then, again, what we do is we say, okay, we're going to find the present worth, excuse me, over a period of n years, and then we again add these things. So this is the first year is A, second year is A square times A plus J, because A would have increased to a different, by A plus J. The next year it becomes A cube times 1 plus J square, and then it is, this A is still the same as the previous A. Okay, and then on top of it we also have 1 plus J, and then 1 plus J square. Now this is the first year, end of the first year. This is end of the second year, end of the third year, and so on and so forth. Because the first year we have some value, it does not change. Next year it changes. So that's why this factor starts to come into picture only after the second year. So we get this equation. Okay. Now, if we go to the next step, we say that S is equal to A times 1 plus J. So this becomes A times 1 plus J is S. Okay. And we take A outside. So A times A comes outside. This becomes 1 plus A times 1 plus J, which is S. And then S square plus S to the power n minus 1. So this becomes another, again, a geometric series. And we know how to find that. So this is equal to write this right here. And again, you substitute things and you get an equation which is this equation right here. And it is in terms of two things. One is the discount rate, which is D, and J is the growth rate. So both things are included. And this actually works for cases where D is greater than J, because D is the discount rate, J is the rate at which things are growing. So if it grows at a higher rate than the discount rate, then this quantity will become negative. So you have to be careful about that. Okay. Okay, so what we can do is I can show you an example to apply these principles to selection of conductors and transformers. So we're going to do some calculations to show you how we can decide. You have a distribution system and you want to select conductors for a feeder. What size of conductor should we select? Okay. So based on economic decisions. So the reason why it is important is that if you have a particular size of conductors, then you're building a new system, so you need to determine what size of conductors you want to use, or you have an existing system and you want to upgrade your conductors to a bigger size because the load has increased. Now, why do we need to worry about it? All these things is because size of the conductors is very important, because two reasons. One is that when you buy conductors to put on the line, if the conductor is bigger, it has more metal, so it's going to cost you more, and it will cost you more to install it. But on the other hand, the benefit that you're getting is because a bigger conductor, what are the things happening in a conductor? When current flows through it, what will it do? What's that? Losses. Yeah, it's going to have losses. The losses are I square R. Okay? And R is a function of the size. Your bigger conductor will have lower R, smaller conductor will have higher R. So if you have if you buy more expensive, something that is more expensive, you can have less losses. But the point is that how big should you buy to reduce losses? So there has to be a balance. So that's what we're going to compare here. So how do we do that? We are going to consider the cost of installation, which will one-time cost. You want to buy and install, so that's the initial cost. And then every year you have to do some maintenance work to make sure that everything remains functional, like maybe a replacement of insulator, some kind of like coupling, some kind of mechanical things that hold the things or whatever. There may be some maintenance required on a yearly basis. And then in addition to that, we are going to, so there is a fixed value of maintenance, cost of maintenance. We can assume that maintenance requires the same amount of money every year. So that's a fixed value. So you have initial cost, then you have every year you have putting money for maintenance. And then the third option, the third item is the losses that take place in the system. So losses are dependent on the resistance. So in the transmission, in distribution systems, we don't do any transposition. Are you all familiar with transposition? In the transmission lines, you change the phase positions to balance the system. Now, in distribution system, that is not very practical because within the city, it's very difficult to do any kind of transposition. So you don't do that. So as a result of that, a three-phase line is going to be unbalanced. Because phase A, B, and C are at different locations, so they are coupling and their values are going to be different. So in this case, what we do is we say that because they are untransposed and the calculations have to be done, if you consider the entire matrix of the three-phase line, the calculations becomes overly complex. So we want to simplify things. So there are two possible ways to do it. One is to just assume that the feeder is transposed and then determine the sequence matrix. And then from that, you can use the positive sequence values that you get for the calculation of the line impedance and assume that all three phases are going to be identical. The second approach is to just ignore the mutual impedance and you have phase A, B, and C. Just take the average of the three and use that for the calculation. Now, both ways, the values that you get may be slightly different from one another, but for planning purposes and such calculations, we typically don't need to worry about being overly accurate about what you do. So long as you are within 5%, 10% of the actual values, it's okay. So this is kind of like any engineering is imperfect. There is nothing perfect in engineering. Even if you do calculations with power flow calculations or any kind of analysis that you do in power systems, you are making some approximations. The models are not correct. All models have error. There is no perfect model that's available. So similarly, in economic calculations, we can't be perfect about everything, so we assume certain things. Okay, so this is one of the assumptions. So with that being the case, we come to this position here, where we have to account for losses. So assuming that we have found the impedance of the line, which is R plus jx, R is the resistance, x is the reactance of the line, which is a standard process to compute those because there are equations available. You can calculate those. And I'm not going to worry about that. I hope you know how to do that. And then let's assume that the peak load in the first year of operation of the line is P megawatts. Okay, so we are given information that the load on the line is, we have to select conductors for a load of P megawatts in the first year. So we say, okay, how many losses will be there? So first we calculate I, which is P is in megawatts, you multiply by 10 to the power 3. Voltage is in kilovolts, so that's why this 10 to the power 3 factor has to be included, because P will be 10 to the power 6, it will be 10 to the power 3, so that will cancel out and you're left to 10 to the power 3. And square root of 3 times V is the line-to-line voltage, the power factor, so this gives you current, okay? And then the loss three-phase line, okay? In the first, this is what we are doing is we are calculating. Okay, here is what we'll do. So we need to find out loss for the entire year, okay? Given that this is the peak value, okay? So at peak, we can compute 3 times I square R. So this is I. You take the square of this. So that becomes P square. And you multiply that by R. It is 10 to the power 3 P square multiplied by R. And then the square of V times PF, you square that. And then you have 3 phases. A, B, and C. So each phase will have loss. So you multiply by 3, and that 3 is going to cancel with the square of the square root of 3. So 3 and 3 will cancel. And then you multiply that by 8,760 hours. That's in 1 year. And then you also multiply by LSF. This is the loss factor. In the previous chapter, we talked about loss factor, which says that if you know the losses at the peak value, you can estimate the losses for the entire year using loss factor. So that's where it comes into picture. And then you have this equation right here, which can be represented as D times P square. Now remember that D is just nothing but the rest of the quantity right here, and which is given, if you are given all these values, it is a constant. Okay. So this is the losses in the first year. Now let's assume that the load, and of course then you multiply by this is in megawatts or whatever the units that you have. This is kilowatt hours. Okay. So kilowatt hours per kilowatt, this is 1 unit. So how many money, cents or dollars or rupees that you have to pay for each unit, you multiply by that and you get the cost in terms of money. And then we assume that the load is going to grow at a rate of M per year. So Pn, load in any given year N, is going to grow at a rate of M. Okay? And then the question is that the losses are going to grow at a rate of square of the power. Okay? We had talked about that earlier, that current is proportional to power. So I square is proportional to P square. So if the P increases by a certain amount, the losses are going to increase with the square of that amount. So this becomes losses will grow d times p to the power n square, which is dp square times 1 plus m raised to power 2n. And then when you break it up, you find that the losses will grow at the rate of m square plus 2m. Okay, because of the square. So this actually j becomes m square plus 2m. And this is again, m has to be in terms of fractional value. So if m is growing, the load is growing at a percent to 2%, then it's 0.02. Okay. Okay. So then we actually come up here and then say that, okay, loss in year n is lost in your first year multiplied by 1 plus j to the power n. So we can estimate the losses in the future years. Now typically what happens is that in utility business, the losses, the load does not keep increasing for 30 years. if you build a system, for example, a distribution system, initially the load is low, it will keep growing, and another 5-10 years it will come to the maximum value. But then after that, it does not grow anymore. So it has an increasing trend and then it stops growing. So we can actually calculate the value of losses that are growing up to 10 years, increasing, and then it remains the same. So you break the calculation into two parts. One is for the years when the load is growing, and then the rest of the years when the load is not growing. So you take those two equations and you come up with a summation of the two. It's like a little bit extra calculation, but it's not very difficult to do that. Okay? And then we combine all these things and we come to a point where we find that the total cost of the conductors is equal to A plus B times P square. Okay? Where A is it includes the initial installation cost plus the present worth of O&M over a period of whatever the cost, number of years that you are considering. And then B is equal to the, this is equal to the cost of losses due to losses. So every year you have losses, and this PW2 here is the quantity that you multiply the first year losses by this quantum right here, because this includes the fact that the losses are increasing every year by a certain amount because the load is growing. So this then becomes an equation which is actually a quadratic equation, A plus B times B square. So whatever the load is, peak load, remember that P is the peak load in megawatts, and this is per mile because we considered the resistance to be for 1 mile. Okay, that's why it is per mile. Okay. Now the next thing we're going to do is use these equations and calculate. We have the different options for conductors. The data is given by manufacturers. We look at the data sheet and we have the resistance value available. We have all those data available. And based on that data, then we come up with of course, we have to be given the cost of installation. We have to be given O&M cost. All those data has to be given. And then we can plug those things in and then plot the equation. So this is what happens. So when you plot different conductors, you get a graph that is shown at the bottom here. And what is interesting is that the conductor, which is the cheapest, will rise, it will have a steeper graph here because its resistance is higher, so it has higher losses, so that graph goes up at a faster rate because that coefficient B is bigger in that case. So, and then you draw these graphs, and what we find is interesting is that these graphs are going to intersect one another. So what makes it useful here is that if you were interested in selecting a conductor where the peak load happens to be between P1 and P2, then the best conductors that you can get with the minimum, this is the cost right here in the y-axis. So for any load that is between P1 and P2, the initial peak load, then this conductor, which is number 3, becomes the best conductor. Although conductor number 1 obviously is too small, conductor number 2 is still okay. You can use conductor number 2, but it's going to cost you more on the long run. If you combine everything together, its total cost is going to be higher. So the key thing here is that just because something is cheaper, it doesn't necessarily mean that it is the best option, because you have to consider everything, all the aspects together of cost. Sometimes you buy something which is very cheap, but it doesn't last you very long. So then you say, okay, every year, 2 years, you have to keep replacing it. But if you buy something better quality, more expensive, then it can go for longer duration. So in this case, it's not the quality is not the issue. It is just basically the fact that bigger conductor is more expensive, so it has less losses. So you have these graphs right here. So what we do is we define what is called economic loading range of each conductor. So conductor number 3, for example, has economic loading range that goes from P1 to P2. Now similarly, conductor 1 goes from 0 to some value here. Unfortunately, conductor 2 has a very small range here. And then anything beyond P3, conductor 4 is the best one. So what this allows you to do is compare the cost, total cost of different options. Okay, what is next? The next is we are going to define something here which is called the reach of feeders. Okay. Now, reach of the feeder is basically that the fact that if we, as you remember in the previous lecture, I told you about maintaining a proper voltage for the customers at the end of the feeder. So what we want to do here is if you have a specific conductor, it's going and it's supposed to carry certain P megawatts of load. It's going to have some losses that will take place, but what else will happen on the feeder when the current flows on it? Anybody have an answer? If you have R plus JX and you are sending current into it, what happens? You have I square R losses, but there is something else happening. Would you say? What is that? Voltage drop, exactly. Voltage drop, that's what I was looking for. Voltage drop. Ohm's law, R plus Jx times the current, the voltage is going to drop. So if you have a very long feeder, then by the time you reach the end of the feeder, the voltage is going to be too low, which means that you're not doing a good job. So there is a maximum length of the line up to which you can provide proper voltage. So we define this quantity as the reach. So if we say that a feeder has to carry so many megawatts, then the length up to which the feeder can provide power without losing, going out of the range, is called the reach of the conductor. So what we define is the reach at different values. So first thing we call is the thermal reach. Thermal reach basically means that you want to load the conductor to the maximum value, which is, if you look at the previous graph, conductor number 4 can go all the way up to here, which is the maximum load that it can carry. And at the thermal limit, whatever the P happens to be, you calculate the reach based on that, and we call that as a thermal reach. Now, on the other hand, economic reach is defined by, like for example, if you're looking at conductor number 3, it can carry power from P1 to P2. So the maximum power it will carry is P2. So the economic reach of this conductor is calculated based on P2. Just the maximum P that you want to load with that particular size of conductor. So that's what we call as the economic reach. It can carry more current, but we don't want to overload it because that basically makes it less economical, and you're unnecessarily penalizing that conductor, so it's not worth it. you need to, or essentially it means that as soon as your peak load exceeds this value, you need to go to the higher size conductor. So this is economic reach of the conductor is defined as the maximum value which is in the economic range. Okay, so that's what I have defined here: thermal reach and economic reach. And then what we're going to do is we are going to do some calculations for voltage drop, because we want to calculate reach of these conductors. So we're going to do some calculation on voltage drop. So again, approximation. Approximation is always the best way to do it, because you can't be doing too many detailed calculations in some of these things. So let's assume that we have sending end and receiving end, and the line has an impedance R plus JX. We ignore the shunt elements in distribution system because they are not very large. For small, low voltage systems, those are not important. Transmission systems, you need to have that. And then what we simply do is we say, okay, voltage at S is equal to VR plus I times R plus JX. Very simple equation, circuit equation. And then we say that difference between the voltages is voltage drop. And then we draw a phasor diagram here, assuming that the current is lagging the voltage. So we have phi is the angle. And then based on the load that's connected here, and then this is the voltage across along the resistance voltage drop, and this is the JX part here, I times JX, and then this is VS. Now, typically, we assume that voltage at the receiving end has a zero angle, and we look at this equation right here, and then we write this equation, which is Vs cosine delta, like break it up, because this is a phasor, Vs is phasor value. So we convert that to real part and imaginary part. So this becomes Vs cosine delta plus J Vs sine delta minus Vr. And then same thing we do here, which is to break this up in real part and imaginary part. And this is what comes out to be the case. Now, typically in a distribution system, R is approximately equal to K, equal to X, and delta is very small. Unlike transmission system, distribution systems have very small delta. So as a result of that, cosine delta becomes 1 and sine delta becomes 0. So which basically means that we can put cosine delta equal to 1 and sine delta is 0. So the imaginary part actually is almost 0. Very small. So we neglect that. And then once we do that, we can see that the approximate voltage between Vs and Br is equal to I times R cosine phi plus X sine phi. Very simple calculation here. So once you know the power factor of the load, which is cosine phi, you know the resistance, you know the reactance of the line, you know the current, magnitude of the current, you can calculate the approximate value of voltage drop. A very simple calculation to avoid doing too many of these calculations. Okay, and then what we do is we say, okay, now what we're going to do is we are going to calculate voltage drop in percentage voltage drop per mile, because the assumption is the load is balanced and all the phases have the same impedance. I told you in the beginning that we're going to assume that to be the case. And then you have voltage drop is R cosine phi plus X sine phi. And now this is on a per phase basis. We are looking at each phase. So this voltage is line to line voltage, and that has to be divided by square root of 3. So square root of 3, this is a line to neutral voltage, and a square root of 3 goes up there. And 1000 is because the upper equation is in volts and lower one is in voltage is in kilovolts, so you convert that to volts and then multiply by 100, so this gives you voltage drop per mile. Okay, and then what we do is we say, okay, we have this these are the line conductor values based on economics, and now we are going to calculate the reach of the conductors. And how do we do that? We basically consider that the voltage drop is allowed voltage drop is delta V. Okay, so we say that from the substation to the end of the line, what is the voltage drop that is allowed? Now, typically in a distribution system, delta V is 7.5%. So because, again, is this working? Yeah, I think. The reason is that, as I said, you have 120 volts is your nominal. You have plus 5%, minus 5%. And assuming that you are operating at the higher end at the beginning, you can go 10%, but we allow 2.5% as a margin. So with the margin, we say, okay, we're going to allow only up to 7.5%. So that's acceptable. So to 7.5% voltage drop is allowed. So if delta V is 7.5%, and you know that the voltage drop per mile is given, then you have 7.5% voltage drop, you divide by the voltage drop per mile, and it gives you answer, the reach is in miles. Okay, and then you can convert that in terms of by substituting values, you can actually calculate the reach in terms of P, which is the megawatt value that you are putting on the line. Okay, that's basically a simple conversion of I to P. P is the three-phase power that the lines are carrying, and based on that, you can change these to show them in terms of PCB. I won't show the details, but that can be done. And then you can compute the reach values at different current values. You can use you can find the economic reach. You can find the thermal reach based on different loading. Now, one of the things that is important in this one is that when you compute reach of a conductor, we have two values of power. One of them was, I think, let me see. I think these are some notes that you can check. We can talk about this in just a minute. Okay, one of the things that is important to keep in mind is that this P that you see here, so higher the P is, the lower the reach is going to be. The reason is that you are putting more power, which is more current. That means that the voltage drop is going to be higher, so your distance has to be reduced. Okay. Now, also keep in mind that the economic calculations that we did used P in the calculation here is based on the initial load, but load is growing at a certain percentage. So when you calculate reach, you must use the final value of the peak load, not the initial value. For economic calculation, you use the initial value. For reach calculations, you need the final value. So that is very important. And then we typically like to keep the reach of all the conductors to be the same. So I'm going to talk about that in a minute. And then let's move to the next slide. Okay, now this is a graph that shows that different conductors can carry power at different power values. You get different reach values because conductor number one, you have minimum to maximum value of P. You substitute that into this equation and then you come up with this graph. Same thing for conductor 2, conductor 3, conductor 4. And what you find is that for different loading values, you have different reach values. And then if you want to have the common reach, then because what we are saying is that we are given a system, we want to build a system for, you have a substation here and the maximum distance that we have go is 5 kilometers or something. So that distance is known to us. We can go that far. So now we want to decide which size of conductor we need to use to do that. So there are two factors. One is the cost, one is the reach. So this is a balance between the two things. So, and then for the fixed reach, because once you know that what is your distance, then you can, from here you can find out what would be the reach of, what would be the loading of the conductors at that reach value. So if you have a fixed distance, then you can, for each conductor, you have how much it can carry to reach that level, okay? And then we go to the next slide. I think, so we draw a line here to show the common reach, and of course, I think this is, we already talked about it, so I'm going to skip to the next one. And here is what I was mentioning, that the correlation between what you see in the graph here, which is calculated based on, so the P1 value and P max 1 value are not the same because you actually have to use the formula here that P1 will actually become something else in n years. It will grow to something else. So in the calculations that when you are saying that you have, for example, the conductor number 1, it can carry, for this reach as an example, it carries P max 1. That's the maximum power it can carry. So what is the corresponding P1? Corresponding P1 is, which is in the cost calculations, it is P1 is P max 1 divided by 1 plus m to the power n. So you have to bring it back to the first year, because the calculation for the cost calculations were based on the load value in the first year. The reach calculations are done with the P value, P max in the last year. So you have to match the two things. And then what happens is that we take these values and then we say, okay, now remember that we had the cost characteristics which were shown here, okay? And then we find out that although conductor number 3 can go from P1 to P2, but it will not provide you enough reach at P2. So it will have to be truncated at some value which is in between. So that calculation that you do from the reach graphs, you find out what is the value at which we need to, the reach of it reaches its maximum value. Okay? So then what we do is we say, okay, we're going to find those and we're going to draw a new graph. And so this is conductor number 1, and then number 2, number 3, number 4. So this graph actually shows the 4 conductors with the cost associated with the reach, because instead of intersection between the conductors happening at the economic point, now the reach has become a factor too. So it doesn't quite go up to the intersection point. It has a jump before that. So the graph becomes modified based on these calculations. And then what we find is that this is the modified characteristics, cost characteristics for the conductors while accounting for the reach that you're interested in. Okay? And then what we say is that if we were given a choice and we were able to draw a straight line here, which would be considered the ideal characteristics of the conductors, then we could possibly get the best conductors to meet our requirement. But it's not possible to get ideal characteristics because it is because of the way the conductor characteristics are. But we can try to get as close as possible to this line as much as much as we can. So this particular line is actually a tangent line, which is tangent to the first conductor, and the last conductor is not shown here, but if they extend the last conductor, it will kind of create can draw a tangent line. So the idea is if we were to select 4 conductors given all the data, then you can select a conductor set which is as close as possible to this line as you can come. And then by doing that, we can define what we call as the optimal set of conductors. Now, because these are some of the details in the calculations. Okay, so this, for example, the calculations shown in this section as well as the previous section are for 3-phase feeders. This can be modified for single and 2-phase feeders. I didn't show you that. And then in some cases, there are single-phase feeders, so we can modify that to include them. And then the voltage drop calculations were done with an assumption that the power flowing on the feeders remains the same at the beginning and at the end of the feeder, but in reality the power flow decreases as we move along the feeder because the feeder will have lateral step top. So this is again an approximation that we are assuming the feeder to have the same load. We could actually modify these calculations if we have given more information about in terms of what type of load area the feeder is serving and so on and so forth. But some of these conditions actually will not change the calculations a whole lot, but they will make things more complicated. So we don't worry about it. Okay, moving along. So one thing we can do is if you want to decide on a good set of good conductors, like you are given all the data and say, okay, I need to pick 4 conductors that were the best 4 conductors, because you have a choice. You have 20 different conductors available from the manufacturers. Which one should we pick? So one option is to use this graph and calculate the area between the actual load characteristic that you see here at the top, the ideal line, we calculate the area. But one thing you have to keep in mind is that we can calculate the area, but the area has to be weighted, because if all the conductors in the system were to carry the same amount of power, then it's okay. But what we find out is that there are more conductors with lesser power compared to the conductors that carry more power. So the weights have to be adjusted. And so what we have done here is to give you an example. I think I'm going to move faster here because we need to do a little. Okay, so this is the equation that x1 and x2. The what I was talking about, that you can draw an ideal line by finding x1 and x2. So because let's see, go back here quite quickly. What we need to know is we need to know this point right here, and we need to know a point up there. So this is x1, and that's x2, and those can be calculated based on the if you have y1 is the smallest conductor, y4 is the biggest conductor, then x1 and x2 can be computed using these equations. Again, I'm not giving you the proof, but that's something that can be done. And then what happens here is that we will consider an example to show you how this can be applied to a real system. And in this case, what we did was we used data from a utility which had to 24,800 miles of primary voltage line. And what was found is that 56% of the total length of feeders carry power less than half a megawatt because they are single phase laterals. Okay? And then 11% of the total length of feeders carry power less between 0.5 to 1 megawatt. So what we did is we decided to ignore the feeders that had less than 1 megawatt because those are single phase feeders. So the next slide, I have the data here. And so what we did is we ignored the conductors that were here, and then we computed a new values of percentages after discarding the first two rows here. And then what we did is we said because these percentages are different, because conductors that are from 1 to 1.5 megawatt, they are more of those. So the point is that if you emphasize conductors of different size to have the same value, then you are not doing the right calculation. So what we need to do is we need to bring the smaller conductors as close as possible to the lower line, and the larger conductors, because there are only few of those, even if you don't do a very good job of selecting the right kind of conductor, your losses are not going to be that significant. But the smaller conductor needs to be, because there are more of smaller conductors in the system compared to the larger ones. And then what we do is we calculate the average area between the conductors that you have selected versus the straight line, and then weight them based on which range of load they follow in. So for example, 1.5 to 2 megawatt, there is a separate weight, and then it goes through a process of integration, and so some details are given in this slide. I'll just skip that. And then this is an example which is based on a published paper that one of my students had worked on. And what we did is we used two different approaches to compute or determine the best conductor set. One was the condition where you find the best set and then you adjust the reach based on what you're interested in. The second approach is that you before you find the best set, you first adjust the reach and then find the best set. So method A and method B, we applied that to for 4 conductors as well as 5 conductors, and we came up with the best conductor set, which are a little bit different from one another. For example, method A gave a slightly different answer compared to method B. And uh, also then in the next step, what we did is we said that we want to fix the reach to be equal to 4.7 miles. And then you, okay, let me give you I think this is, you can read through some of the details of this. I don't think I have a lot of things to do here. So, okay, I think I'm going to go to the next step now. So, and then what we did is we said, what if we reduce the reach a little bit from 4.7 miles to 3.6 miles? And we found that once you do that, if you reduce the reach, the conductors that you select with method A or method B turn out to be almost the same. Okay, generally, we find that method B is better than method A if reach is known ahead of time. But both methods give the same result for shorter reaches. And that's what I wanted to show you. Okay. So, anyway, and 5 conductors are better than 4 conductors, but then the drawback is that the utility company has to maintain 5 different conductors instead of 4 conductors. So that will add to the cost. So it's basically a trade-off. So that actually is a conclusion about selection of conductors. I think it was kind of like a overload of information, but a lot of details are given in the slides. When you get those, you can read through them. So let me quickly move to the next topic in our discussion, which is economic evaluation of transformers. And this one is an important thing because how do you decide on the size of the transformer? So again, transformer has capital cost, annual charge rate, which is basically same as the present worth, inverse of the present worth, and then annual operating expenses. So the total annual cost of transformer is given by uh, the capital cost multiplied by AR, which is now in this case, what we are trying to do is we are trying to convert everything to annual cost. So whatever the capital cost is, we are converting it into, in the previous example, we converted annual cost to present worth. Now this is the reverse of that. Because we have the fixed cost to buy the transformer, we are converting it to how much is the annual cost. So this cost of transformer is multiplied by a factor which is the reverse of the present worth factor. And then this is the operating expense. The operating expense of a transformer is basically in terms of losses, because transformer will have losses. And there are 3 types of losses: cost of exciting current, core losses, and copper losses. The combination of the 3 of them. And then the excitation losses are IEX multiplied by KVA times CSC times AR. I'm going to explain those. IX is the per unit exciting current of the transformer. Excuse me. KVA is the nameplate rating of the transformer. And CSC is the installed cost of per kVAR of the primary shunt capacitors. So the way we are estimating this cost is by saying that the excitation is inductive, and how do you cancel that with capacitors? So if you were to cancel the inductive part with capacitors, what will it cost you to do that? So the cost is actually calculated based on that factor. You're not actually putting capacitors, but you are trying to compensate by saying that this is the cost associated with that. And then we as far as the cost of capacitors needed to compensate the inductance caused by the exciting current in the transformer is given by this is CCW, which is let's see. So this is the excitation cost, okay, and then we are computing the cost of capacitor needed to compensate the inductors caused by the exciting current, and so that's what it is. And then CCL, which is the next part of the cost, which is due to uh, core losses, and then the third one is copper losses. The core losses are equal to CW times AR plus Cgen times H multiplied by LCL. Where CCW is the cost of investment per kilowatt of load, and then Cgen is the cost of energy generation per kilowatt hour. So what happens is that when you are accounting for losses, there are two things to be considered. One is that if you have extra losses, these extra losses have to be covered by extra generation. And that extra generation can be accounted for in two ways. One is the kilowatt value, which is at the peak. If the losses happen to be at the peak, then you want extra generation at that peak to be able to account for that. And then you also have energy losses which are throughout the year. So you have to account for both of those things. So this one is the CCW is the cost of investment per kilowatt because we have to generate extra power. And then Cgen is the cost of energy at this number of hours, and LCL are the core losses with kilowatt. So that's why we have cost with respect to kilowatt and kilowatt hour, both of them. The same thing for copper losses, which is the CWAR, and then CPgen, number of hours, and then this is CPgen is the incremental cost of the peak generation per kilowatt hour, because what happens here is that the core losses are fixed, they don't change. Whereas copper losses change. Copper losses are higher at peak and lower at other values. So that's why we use the loss factor here again, like we talked about in the previous situation. And then, so we use the cost of generation. Now this is the cost of generation under normal situations. This is the cost of generation under peak situation. And we have number of hours, and then we multiply it by loss factor. And this is P square is the peak load, and then LCU is the copper losses. Then we add all of them, and then we come up with an economic performance index, which is ACT divided by kVA. So the total cost over kVA. That's what is defined as the economic performance index. And then we have the next slide, which is an example of, this has all the data for the transformer. All we have to do is plug the values and then come up with an answer, which is $12.48 per kVA is the economic performance index. So if you have two different transformers, you want to compare one with the other, then you can do all the calculations and find out which one is the better transformer. So the next topic in economic calculations discussion is tariffs and pricing. So utilities have to charge customers for the electricity they sell. And this is something they, I don't know, I think in India many of the companies are government owned, but there are some private companies also. But generally in US, the distribution is all, everything is private. So what they want to do is they want to invest money, and then that has to be recovered by charging to the customer. So there are different models that they use for pricing of electricity. So I'm going to talk about those, and different utilities, different states have different models, so this is a general discussion that I want to have. So there are charges associated with kilowatt hour, how many units of electricity that you consume, and then also sometimes there could be a charge for demand. What is the maximum demand in kilowatts over a period of time? And then there are time of use rates where the electricity is more expensive during the day because it's more expensive for utilities to generate electricity during the day. So you could have from 2 o'clock in the afternoon to 8 o'clock in the evening peak value, then you can have shoulder value and low peak, off peak. So these are some of the options that are available. And then there is critical peak pricing, which basically is instead of using TO time of use, they use critical peak pricing, which is applicable only on a certain number of days in the year, maybe about 15 days or something. And then if the utility expects the next day to be very severe in terms of the demand as a forecast, because it's going to be very hot or something, so they can declare a critical peak day. So they can send a signal to the customer saying that tomorrow is going to be a critical day, so you should reduce your consumption, because the rate of electricity then actually jumps by 10 times or something like that, becomes very high. So, but that's only on very few days of the year. So what the utility does in that, because they are charging you a lot of money for a few days, they give you a discount for the rest of the year to compensate for that. So that's one possible option. Not many utilities use it, but some of them have tried that. And then there is critical peak rebates. It's, instead of critical peak pricing, this is critical peak rebate. So if you provide, like for example, they say this is going to be a critical day, and then you reduce your consumption in that period, then you give you a rebate. It's the opposite of that. And then there are interruptible rates, which basically the utility, it's not for individual customer, for businesses. They can say, okay, we can give you a discounted rate, but at the same time, whenever there is a need, we can disconnect you. So on a certain number of days of the year. But most of the times, there will be some kind of alert given. It's not like all of a sudden, but they say, okay, how about tomorrow is going to be a critical day, so we're going to interrupt your load or something like that. Then there is power factor based rates, where the power factor, if it deviates from a certain fixed value, then they can put extra charges on that. Real-time pricing is actually something that is being discussed now. And at the transmission level, we already have real-time pricing, but at the distribution level, we don't have it yet. But it is possible that in the future it could come into picture, because as more and more customers start putting solar panels in their homes, and if they generate extra electricity, they want to sell it to the utility, then what is happening now in the US is that third-party aggregators have been given permission to combine multiple customers and then sell or buy and sell in the market. So in those cases, they can possibly see real-time pricing. Now, net metering is another thing that is important, because net metering is an idea that in the old days, the customers were just buying electricity, not selling. But now they are generating extra electricity which can be sold. So, but when you actually buy electricity, you're not just paying for generation of electricity, but you're also paying for the transmission of electricity. So when you actually generate your own electricity, the utility company is not going to give you the entire amount as a credit. They give you only the part which is applicable to the generation part, not for everything else. So the net metering basically means that the buying and selling rate is different for individual customers. It's not the same. Of course, different companies and different states have different models for that. So, and of course, an electricity bill, this is an example of how the electricity bill from one particular company in the US. So they have different rate for June to September and October to May. First 800 kilowatt hours, they have a different rate. And then over 800 kilowatt hours, they will charge you a little bit less. So this is for bigger customers, not for small customers. And then they would have generation charges, extra charges here, transmission charges, all those things. So this is a breakdown. And then the next slide shows an example, which is customer consumes 1125 kilowatt hour in the month of July. And basically what we are doing here is we are simply doing the calculation which is based on the rules that are given in the previous slide. So I'm going to skip the details for you to look at. Okay, so all we have done is using these rates, it is notice that first 800 is at a higher price, so we come up with just $16.86. The next 325, because it's 1125, so 800 plus 325 is a lower rate. You can come up with a number. Similarly for generation, we do the same thing. And then transmission is 1125 is a fixed rate. It doesn't matter. So we use that. And then, of course, the customer has volunteered to purchase 500 kilowatt of electricity per month from solar resources and pay a surcharge of 2.055 cents per kilowatt hours. In addition to kilowatt hour usage, the utility has determined a fuel charge of $21.65 and taxes of $6.13. So this is the green power charge of $10. So the monthly bill is a combination of all of those. It comes to $113.03. And the average cost of electricity for this customer is 10.051 cents per kilowatt hour. Okay. So just a few more things here. Now, all the examples that I gave you are based on the normal utilities that are for profit. But in US, there are also two different kinds of other types of utilities. One is called the Rural Electric Cooperative. And these were created in 1936 because when the electricity systems were growing, what was found out was that these companies were not focusing in rural communities. They are mostly focusing on urban communities. So the government actually created this concept of rural electric cooperatives, which are non-profit organizations. They take care of supplying electricity to rural communities. So they are like, they are actually the cheapest of all the distribution companies in the US because they are non-profit. And large part of US is served by rural electric cooperatives. Also, municipal utilities are there where there are many small cities. They don't have capacity to buy, they generate their own electricity. And the big companies are not interested in providing service to them, so they themselves buy and sell electricity. So the city, for example, I think in US, in India also, we have a few, like Kolkata, I think has their own distribution, some parts of Kolkata. And Ahmedabad, I know it's a separate company. It's a private company there. So these are municipal utilities. There are in the US, we have cities of 800 people, 1,000 people, very small cities. So they just buy from wholesale providers and then they sell it to their consumers. So I think that is basically all I have. Questions? Yes.
Pricing method adopted by USA is
What kind of pricing?
method adopting in USA as you.
Okay, it varies from different company to company because, as I said, in USA we have different types of. One is called investor-owned utilities, which is like a private company where their goal is to make money for profit. So they will charge you a certain rate where they can make some money, and then it all depends on the time of use rates and demand charges and all those things are dependent on sometimes each utility will have its own plan. There's no fixed value. So, and then you have a choice. Like, for example, my house, we straight away pay for kilowatt hours. We don't pay for anything else. But they also have an option where we could choose to use demand-based rates. So what happens in that case is that they will charge you for demand, but at the same time they'll give you a discount on the energy. So it's up to you. Like every city will have a different rate that's available to customers. So there is no fixed formula for it. These are some examples. Any other question?
Sir, how many electricity in your
How much is the
area?
theft in US? Theft is actually not as big.
Like line bypass theft, how we can manage? Like metering is advanced, but how we manage line bypass theft?
Line bypass theft is like somebody puts a conduct.
Line bypass means from pole to metering. In between, we can connect or the line bypass.
Oh, I see. That's what I mean. That hook something and then bypass. We don't see that happen there very much. It doesn't happen. Could be in some rural communities, get some like isolated cases, but not really much of a problem. I know it's very common in India, I think, but in US it's not there. And meter, you cannot do anything anymore because all the meters have become electronic. So theft with meters is almost impossible. Otherwise, in the old days, they would put some kind of magnetic devices to stop the meter from moving and things like that. But now that also cannot be done anymore.
They are considered for design of conductors in distribution system.
The load growth,
Period. How much and value?
N value. Okay, okay. That's a good question. I think that typically conductors can go for 30, 40 years. So you can easily consider 30 years without any problem. Or sometimes even 40 years will be okay. But most utility planning, they use about 30 is a very common number. For any other equipment, for solar panels, 20 is more common because solar panels, their life is about 20 years. Yes.
You have comparative idea of maintenance cost of overhead line versus
underground line?
Overhead versus underground.
The maintenance cost, not the installation cost.
Maintenance wise. Okay, I don't have the actual numbers. So I know that to build an underground line, it cost you 5 to 10 times more. I think underground lines perhaps don't really need any maintenance. Only thing when
Definition of fault is very challenging, so every time you have to dig up.
that's right. I think when a fault takes place, it becomes harder because then you have to dig up. But I think there are some new techniques that are available, and they actually also it depends on how the lines are laid. If you have direct burial or you have conduits or something, so if you put conduits, then it's easier to fix things. If you put direct burial, then you have to dig. So it all depends. But underground line, that is exactly the problem. But for a regular maintenance, I don't think they need anything. Yeah, it's only when emergency take place, some problems happen. But overhead lines need more maintenance because they are prone to fire on objects and other things falling and things like that. But I don't have the exact numbers on those things. Anything else? That okay? All right. So I hope you got something from today's lecture, and tomorrow Professor Sharma is going to teach, and I will come back again on Wednesday.